can I start? Yeah? Yeah, okay. So, yeah? Okay. So, thanks for coming. So, I'm Mathilde Lemée. I'm a Java developer. I used to work for Terracotta. So, Terracotta is in-memory data grid software, and it's the company behind the Cache. Okay. So today we're gonna talk about basics of cache. Okay, different patterns to read and write the data into a cache. We're also gonna see what is an in-memory data grid. How many of you knows what is an in-memory data grid? Okay, and we're gonna compare in-memory data grid, distributed cache, and NoSQL stuff, and SQL stuff too. Okay. So. I guess that everybody knows this picture, okay? The higher you get, the faster you go. So one CPU cycle is faster than one access to the RAM, one access to the hard drive, for example, okay? Let's see that a little bit differently, okay? Okay, so there's a lot of things on this slide, but you've got the latency, everybody knows them. What is really important is the scaled timeline. If we say that one CPU cycle is 1 second, okay, just keep in mind that one DRAM access will be 6 minutes. And if you want an access to a SSD, it will be between 2 and 6 days. And for an hard drive, it will be between 1 and 12 months. Just keep this memory in mind, okay? That's why we use cache. We want to be fast. And the difference between 12 months and 6 minutes and 2 days is big. The question is, so, okay, memory is fast. When we put stuff in RAM, it's fast, sorry. So why can't we keep everything in RAM? Just to know that it's for Amazon. If on the page load time, if it decreases from 1 second, that's what they cost to us, okay? They lose in 1 year $1.6 billion, okay? So speed matters, really, when you do e-commerce, but when you do everything. Okay, so let's say I've got a 100 terabyte data store, okay? I want to store that's capacity. If I use a hard drive, to buy the hard drive, it will cost me that. If I want a SSD, that. If I want RAM, that. Okay, so I get that everybody understands why we can't put everything in RAM. Okay, it's just too expensive. That's the idea of cache. In fact, we can't buy something. Yeah, some company can, but not all of them. We can't store everything in RAM. So why don't we store a subset of them? That's what we call the hot sets. Just think about an online bookshop, okay? You maybe have, 30,000 references on your bookshop, okay? But you know that only 5,000 are accessed 90% of the time. So what you're going to do? You're going to store only these 5,000 books, okay? For the other, it's not that important because they are not accessed a lot, okay? What you want to be really fast is when people want to access to your bestsellers, okay? So you will have really a subset of it and storing the subset in RAM, okay? So we saw why we use cache, okay? We want to be fast, and we agreed to not store everything in RAM, okay? Only a subset. So a cache is basically, just think of a key value store, okay? Like a hash map or a map or whatever. So you get keys and values. You've got for each keys, you only have one values. You can't have duplicate keys with the same equals, doesn't matter, okay? The particular why cache is different than a hash map. So you will do get, put all, get all, and stuff like that. But entries can expire. entries can be removed from the hash map, okay? So that's not something you have commonly when you use a hash map, okay? When you put something on the hash map, it stays forever. It's not the same for a cache. So you all know, are you all Java developers? Yeah, okay, so that's GSR 107. The GSR 107 is the GSR for the cache, okay? It was starting a long time ago and take a long time to be published because of patent, because of lawyer, because of a lot of things. But now it's finished. So this is how you do a cache, or you declare a cache. You just do a caching.getCache. You give the name, you give the key class, you give the value class, okay? You're not forced to define the class, okay? If you want to change the class on runtime, you can. Just some vocabulary. The it is when you do a get on the cache and you've got the value, that's a it, okay? A miss is the opposite, okay? You do a get on the cache and you've got a null, that's a miss. Two other vocabulary stuff is TTI and TTL. TTL is time to live. You do a put on a cache, you define a TTL of 5 minutes. 5 minutes after, the value is expired, okay? TTI is when if the data, you define a TTI of 5 minutes. If the data isn't accessed within 5 minutes, it will be removed. So if you get something that every 4 minutes ask to do a get on that key on the cache, it will stay forever. If it's every 6 minutes, it will be expired every time, okay? Oops, sorry. So this is the expiry type. In fact, in the GSR 107, you've got modified and accessed, so TTI and TTL, okay? So that's basic stuff, okay? Just think about a cache like a map, okay? Simple map that can expire or remove elements on it. So now, how do you access data when you want to interact with the cache? So, if so your app as the cache, get me the key 1, okay? If the cache have it, it just will return, okay? If it doesn't have it, it will return null. And it's your functional data who will deal with the database, will return it, and will put it in the cache, okay? That's really simple. The algorithm is here, okay? You do a get. If the value is not null, you do functional stuff about it. If it's null, then you use it. Here is just a calculation, but normally you go to a database or you use a web service to construct your object. But that's the main algorithm, okay? The things here is that you've got one API for the cache and one API for the database or for the web services, okay. But your functional stuff will have to interact with these two APIs, one for the cache, one for the other stuff to create the data. So here, of course, if you use a cache, you will gain, okay? You will be faster because the first time you ask for the key, it will not be there. So you will not gain anything. But the second time, you will gain it because it will be on the map. So it's a complexity of 1. So you will ask it, you will return it. So you will gain time. You will see that the network decrease a little bit because you don't go and forth to the database. You will also see that your database CPU stays lower because you don't ask it. Okay, so that's good. But the problem with that is that what happens if someone else modifies the database? Okay, let's say that you've got a 6-hour time to live, and someone at 3 hours modify the data on the database. Your application will not be able to see it because it's in cache, so it will not be updated. Okay, so you will have a desynchronization between your cache and your database. Okay, the cache will have an older value than your database. Sometimes you want to avoid that, okay? So one thing you can do is to use your cache as the primary system of record. Okay, so first it's reads through. So what you need here is a smart cache. Okay, if you just do by yourself a simple hash map cache, it will not work. But if you use any big open source or not open source cache, it normally supports read-through pattern. So in fact, your application will only deal with the cache, and you will train the cache to know how to retrieve the data. Okay, so your main application will only work with the cache. So you've got only one API. So how does that work? So I will just do the stuff where you've got a miss, okay? So if you get a miss, you've got your persistent layer say, cache, do you have this key? Cache say no, but you train me to retrieve it. So cache retrieve it, put it on itself, on the cache, and return it. So, So you only have one API, and again, you will gain the same hash cache aside. Okay, it will be speeder. You will have a decrease of the CPU load, of the network load. But what's really interesting is, so that's a cache loader. That's how you do it in Java. Okay, if you want to do a cache loader, you just have to implement this interface and so define these two methods, load and load all, and that's how you train your cache to be smart. Okay. At one point, you have to code. Okay, so here is how you do it. So we see how we do it with read. So now how we do it with write is the same. In fact, you are in your application. You do a put with a key and value on the cache. The cache know how to do it. Most of the time, it's in another database, but it can also do something else. But let's say it's a database. And so the cache will write in the database. It will wait until the transaction is finished on the database. It will return to the cache saying, OK, I'm OK. And the cache will start now, when the transaction in the database is finished, to send the new data. OK. Here what's good is that we talked before about desynchronization. Here you don't have it, because everything goes through the cache. So the cache has always the newest values. And because it's a synchronous process between the two, you normally have you don't have desynchronization. Okay, that's what we call natural invalidation. Okay, in cache. If you think about it, this write will be a little slower than written directly in the database. Why? Because instead of writing directly, you will send that to the cache and ask the cache to write in database. Okay, but that's really a small time. So just think it will be a little bit not slower, but it doesn't really matter. Well, okay, sorry. So here's the cache writer. Okay, when you implement the cache writer, you will have write all methods and delete all methods. Okay, so you had to train your cache to do how shall I create a new stuff and how shall I delete a new stuff. Okay, the problem is that that's synchronous. Okay, and I guess that everybody knows that synchronous takes times. And when we do cache stuff, the only thing that matters, not the only thing, but not far, is that we want to be speed. We want to be fast. Okay? So we have a synchronous process. What can we do if we go asynchronous? Will we be speeder? Yeah. That's the white behind stuff. So how does that work with white behind? So you've got the persistence layer that does a put with a key value. Yep. Okay. Let's say it's A. Okay? So you do a put with a key A. So cache say OK. And in fact, instead of putting that directly in database, it will put that on a background thread. Okay? So that's A. Same for B. Okay? Ooh, that should be B. Sorry. Okay, and maybe you will be able to define how many elements you want before flushing them to the database. Okay? Just think a minute. What will we gain here? A lot of things. of course, we are faster. Of course, we have one API. Okay, we already deal with that. But first of all, we do a big request. Okay, instead of doing, let's say, 500 inserts, we will do one big insert with all the data on it. And I guess that we all know that it will be faster, and new database will prefer it. Okay, database usually work better when we give them big requests than smaller one. Okay, and you avoid really doing or sending each time you've got a modify or a create or an update on your cache. You avoid dealing with the database. Yeah. So other stuff you win is completion. Okay. Anyone know what completion is? Okay. So completion. What's a completion? So imagine that you've got 500 keys on the white behind thread. Okay, so you have to do these 500 updates or create. What if, for example, you get 3 times the same key with 3 values difference? Because at minute 1, one of your threads say that key 1, the value associated is B. Maybe 2 minutes after, key 1 to key C to value C, and so on. So what completion means is that it will not do the 3 or 4 or 5 updates on the same key. It will just do one update for each key, and it will take the latest one. Okay, if you've got 5 updates on the same value, it will only put in the database the last one. Why? Because it will be erased. Okay, if we do the 5 requests, the last one will erase the 4 others. So it just do it naturally. It just do completion, so it only takes the last one. Okay, so there again you gain. Okay, you gain because instead of doing 500 requests, if you get a lot of the same data that are updated, it will maybe do 5,500 or maybe lower or maybe higher, but you get completion. Other stuff you get is rate limiting. Sorry, you can define a rate. Okay, you can say that you don't want more than 500 elements per second going through the database. Okay, so what you gain doing that is that if you get very large peak who occurs, okay, you will not have a peak on your database. Okay, it will go like that. Okay, more smaller. You don't have any peak. You can define to not have peak because of rate limiting. So you will also have peak contention, so you can say, okay, from my day, my database or my network are really busy, so I want to write the night. Okay, that's kind of stuff you can do with write behind. So write behind, you will have desynchronization because data will be updated in the cache and not in the database. So it's a limit, but you will gain a lot of things. Okay, and when you really want to be speed, things like that can matter. What happens if my write behind thread fail? The node we handle the thread fail. Okay, I may lose a lot of data. Okay, so if you don't want that your data will be lost, you will write them on the disk too. But again, if you write them on the disk, it will take times. Okay, so when you use the write behind or the write through pattern, you really have to think, okay, what happens? Can I accept that I will maybe lose some data if my server fails? Yes or not? Regarding the response, you will go to a configuration or another. Okay, so just to give you some numbers, okay, about response time. That's so the read are really fast, but that's normal. That's a cache. That's what we want. Let's say that, for example, the write takes 400 milliseconds. Okay, that's why it's true. Of course, I get that. Everybody understands that with write behind because it's asynchronous is kind of immediate. Okay, it's less than 15 milliseconds. Okay. So that just because one is synchronous and the other is not synchronous, one will really be faster. Let's see the database. Okay, that's the database load. Okay, You see with write-through, so write-through is every time you do an update, you'll send a request to the database, okay? So normally the CPU load, so this is an example. If you do a bench, you will be able to see other metrics, but that doesn't matter here. We can assume that it's around a 7% CPU load, okay, and with peak. Okay, what if we do write behind? As I said before, your database prefer big requests than smaller one, okay? And that's the database load, but I could also have shown you the network kilobytes per second, and it will be kind of the same, okay? So, the problem with using your cache as a system of record is that every modify to the database should be done using the cache, okay? What happens if you don't, if it's another entities of your company who do the change in the database? What if it's another company? I don't know. You can't, okay? You can't, because they don't have the cache, so they can't use the system of record pattern, okay? So there is a lot of other patterns. One I want to talk about is refresh ahead. Does anyone know refresh ahead? Okay, so what's refresh ahead? So you remember TTL, time to live? Okay, after 5 minutes, the value expired in the cache, okay? And you have to, after 6 minutes, you will have a miss, so you will end up with asking your database, okay, to retrieve the data. What if we do other stuff like TTR, time to refresh? We also put them at 5 minutes. So between 0 and 5 minutes, okay, everything is normal. You've got the values in the cache. You get a lot of hit on it. And after 5 minutes, you will still have it, okay? If I ask at minute 6, I still have, even if it's after time to refresh, I will have it in cache, okay? So that's a hash map, complexity of 1, really fast. But what's happened is you will also have a background thread that will say that, okay, one key has been accessed after the time to refresh, so I will refresh it. So that's put on a background thread, and on the background thread, you will have the background thread will see on the database and calculates for the key the value, and it will retrieve it and it will put it on the cache. Okay. So at minute 7, if another thread asks for the value, it will have the newer one. Okay. And the cost here is nothing. Okay. Because you don't have a miss. Because what costs a lot is miss. Okay. Every time you've got a miss, you have to go to the database. Here you've got an update that is transparent because it's a background one. So that's time to refresh. So of course you will have a desynchronization between the two, but you don't care because you can define it using a small time to refresh, and you don't pay any cost when the data is updated. Okay, the cost you have to pay when you use time to live, when you really flush the value out of the cache. Here, it will return a value every time, so you gain here. So that was the 4 patterns I want to talk about. And now let's talk a little bit about scalability. Okay? Okay, so I have really no idea what time it is. Okay. So there's a lot of different types of cache. The first one is local. Is really what you have in mind. If you had a local hash map on your Java system, okay, that's a local cache. Okay. A remote is just distant one, and we'll see the other. What about failure? Okay. What about if I have got a remote cache and it fails? Okay. How can I avoid to lose everything? Okay. Because if you get a small, think about a big cache. Okay. A cache with maybe 10 terabytes of data. So that's a kind of really a big one. It takes a lot of time to put 10 terabytes of data in a cache. Okay. So you don't want to lose all your data. So what you can do? You can use a mirrored cache. Okay, a mirrored cache is that you've got other clients and one active remote server, and you will have an antique backup between two. Okay, 1, 2, 3, 4, 5, 6, 7. Oh, there's the 7 as the key. Okay, so you'll see that each key are duplicated in an asynchronous way. Okay. if server 1 fails, okay, what will happen is that you will see an election between server 1 and server, no, not between server 1 because it's dead. So server 2 will detect that server 1 is dead, and it will say, okay, I become the active server, okay? That's what we do normally, okay? But the problem here is that what happens if you get a lot of cache, if it's growing again, at one time you will be out of capacity here, okay? That's just for failure. What you can also do is to have a replicated cache, okay? So here it's synchronous update between the two. So it will be an exact copy of the two, and all the clients can access to one or the other, okay? Run with that. Imagine if you've got 30 servers. If you add two weights that all servers have the value on it, if you get data centers that are one in China, one in US, it takes too much time, in fact, okay? But it's something you can do. So here we see failure, but we don't see scale. So to scale, you get two ways to scale. Okay, you can scale horizontal. Okay, this one is vertical. Sorry. So let's say it again. So you can have vertical scale. Okay, if you want to scale up, you will just take your server and add more processor, more RAM, more disk storage, or everything you want. Okay, but as we see before, it's kind of, you will need some special hardware, and special hardware costs special price, so that's kind of really expensive. Sometimes, think about it, because if you get licenses per server, per node, it can be a good solution. But most of the time, when you go vertical, it's because you're kind of forced to, okay? What if you had to deal with an old database that cannot scale? Okay, you can't partition it on multiple servers. You have only one solution. If you want it to be bigger, it's just to make the server bigger, okay? Because it can't scale. So you're forced to have it on only one server. So you will need to pay the price, okay? But normally, one we used to do is horizontal scale, okay? So to scale out, you will have lots of server, okay? Cheaper, one not really cheap, but cheaper. All kind of the same. The problem here is that you have to maintain a lot of them, and maintaining server has a cost. But because vertical server to scaling up has a bigger cost, companies tend to go to horizontal scale. And now we've got tools like Chef and Puppet and so on to deal with that kind of thing. Okay, maybe a few years ago it was really hard, but now it's a little bit simpler. So you've got your big cache. So what you're going to do, you're going to partition it. Okay, you're going to slice it and thin the slice on different nodes. Okay, that's normally how everybody scales. If you get another way, I want to be aware of it, but that's partition cache. Okay, you get partition 1, partition 2. Partition 1 you get the value for the key 1 and 2. Partition 2 the key 3 and 4 on it with the values. Okay, and you can think about that with a lot of servers. Okay, that's partition cache. And if you want to have more memory in your cache, you add more server. Okay, that's horizontally thing. Oh, sorry, I've lost my thing. There it is. What's up? Just a minute. That's better? Perfect. Okay, sorry for that. So if you want more memory, you add more server. Okay, horizontal scale. But here, if you fail, you lose your data. So let's do the combination of the two. So partition, replica cache, okay? You've got it, so your data are partitioned, send it to each server, and replicated. So here, if this server 1 fails, I get everything I need on server 2, okay? And here on the schema, there is only 2 servers, but normally we've got a lot of it, okay? So you're sure that you don't lose your data, and if something bad happens to one server, another one is able to take the relay. That's different, okay? That's what we do for real. It's more something like that, Okay, so that's a terracotta slide. Okay, that's a commercial one. I didn't find something less commercial. So what we can do here is the server. Okay, it's the server here, the terracotta server array. You can have active and mirror server on it, on its stripe. So that's a stripe, and you get a lot of stripe. Okay, that's all your server. Okay, but what is interesting here is that you also have big memory. That's a cache. Okay, just a cache. Think about it as a cache. You have in fact a local cache. So you have local cache and remote cache. Why? Normally, if your cache are well configured, well sized configured. Here so another vocabulary, here we call that L1, level 1 cache, and here it's level 2 cache. Okay. Level 1 is the same process. Okay. It's the same process. It's the same VM. So access from any value on it is less than 1 microseconds. Okay. It's really fast because it's here. Okay. If you want to go to the L2, you will have network. So it will maybe something like 2 milliseconds, okay? But given the Pareto law, you know the 80-20, normally if it's good size, 80% of the time you will have the data in your L1, okay? 20% of the time you will don't have it, so you will have to retrieve it from the L2, okay? So given that, if we think that here it's 1 microseconds and here it's 2 milliseconds, you've got an average around something like less than 1 millisecond, less than a half milliseconds. Okay, so normally it's kind of speed, and it's what we do. Okay, we have partition, replication, and we've got also local cache, near cache. Okay, and the mix of two gives you the faster way of doing things fast. So just as a configuration, what's great with cache is all of them, the open source and other, when they give you the features to go remote, it's kind of easy. Okay, here is in black is the configuration of a normal cache. Okay, and in the pink is only what I have to define to make it remote, to make it to be able to access it to another server. So, okay, I only give the URL and let's say it's over. Okay. So that's kind of really easy way. When you use a cache, remember that the day you will have to become remote, if you use a good cache, a big cache, you will have the feature on it. Okay, and it will not cost you a lot. Okay, that's a thing that matters. So here is distributed cache versus the world. So in-memory data grid, that's the ancestor of in-memory data grid are distributed cache. Okay, but it's different. It's different in a lot of ways. The goal of an in-memory data grid, okay, it's again provide extreme low latency access to and high availability, exactly as a cache. Okay, the difference here is that with an in-memory data grid, you can store all your data. Okay, you can use it as a cache, but you can also store all your data. Okay, you of course can also do that with a cache, but it's a little bit differently. Okay, the focus changed a little bit because when you have an in-memory distributed cache, you really want to high availability. Okay, so when you use a cache, normally it's on a subset, not the whole cache. You want to be really fast on read. Okay, what matters is really read. When you're dealing with a data grid, it's not really read because it's a data grid, so you can read and write a lot. Okay, the two are optimized. For the the distributed cache, the read is more important than the write. Okay. So in-memory data grid, it's really it was really to make to respond to the growing complexity of data processing. Okay, you don't have the idea of data processing when you use a cache. Okay, with the in-memory data grid, you get it. And now the in-memory data grid, in-memory data grid plus. I mean that they also have in-memory calculate compute grid. Sorry, do you know what a compute grid is? A compute grid. Okay. Think about you've got a big in-memory data grid. Okay, you've got some stuff to do regarding the data. Do you want to retrieve all the data and do your computation on it and eventually send it back, update it to the data store? No. What you want to do is to be able to send your computation on the server where the data is. That's what you get when you do MapReduce and stuff like that, okay? You don't want to retrieve all the data, you will do the calculation where the data is, okay? That's something that is, as an in-memory compute grid, if you really have to do a lot of treatments on data, so especially if you work for bank system or stuff like that, in-memory compute grid can help you to avoid going from the database, retrieve all the data, and do calculation on it and retrieve them, okay? Because on big data, this kind of algorithm doesn't work well. That's why we've got MapReduce, and that's what we also have other frameworks that help to resolve the same use case. Okay, so the idea here is pretty simple. In fact, if job and data are not collocated, really the job will arrive to one remote node. It will say, okay, I don't have the data. Okay, I need the data. Okay, let's go. And it will fetch data and coming back with the data. It costs a lot. It's really expensive. So if you've got two on the same node, you've got the data and the calculation. It's really faster. So it's what we call affinity collocation. Okay, we try to collocate the data and the treatment relative to the data. Okay, that's what a compute grid is. So main feature of the in-memory data grid is that you can have active server and you can have all your servers to be active. I mean, here you don't have any active, passive, master-slave modes. Okay, every node normally should be active. Okay, not all vendors do that. Okay, some vendors have still a master-slave pattern, but normally all servers can be active on each seat. Okay, all the data is stored in RAM to be fast. Normally, you can add and remove server on demand. Okay. The data model is a key value. Okay, so normally it's functional. It's object-based. Okay. You can have, of course, I think it's available in all languages. Okay. The biggest one are .NET and Java, but even if you do other languages, you will be able to find an in-memory data grid. And so the data grid is also resilient. You can have a node that fail and be up again on demand and stuff like that. So that's the main feature of in-memory data grid. There is one thing that is cool, actually, is CEP. Whoops. Okay, that's the Wikipedia definition. So what is event processing? Is a method of tracking and analyzing streams of information. Think about Twitter, okay? What happens if you want to deal with Twitter and every social network, in fact? Because it's live, okay? It's live stream. So you will have constantly new information to deal with it. So what you're gonna do is be able to detect each new elements and to do treatment on it. So that's ACEP. What you've got in memory data grid is the concept of continuous querying. In fact, you will be able to query again. So you will define a query and you will analyze the stream in the input, and you will be able to do stuff and to do calculation on them each time you've got a new tweet, each time you've got a new Facebook messages. Voilà. That's the thing that in-memory data grid and distributed cache too can offer to you, as the ability to work with real stream on real stream. Okay. So we see that we are fast when we go to RAM, to in-memory. Why don't we use in-memory database? I think about, for the smaller one, are H2 and SQLite. Okay, that's in-memory database. What's cool with them is that you have an old program writing with some Oracle stuff or Postgre or MySQL. You will be able to remove your old database and put them in memory. Okay, so it will be kind of easy because in-memory database, it gives you speed because it's in memory. It also gives you SQL because normally it respects the SQL norms. Because, yeah, there is a thing you can't do easily when you deal with in-memory data grid or every other principle. Join, okay, join. Because let's imagine a cache of 10 terabytes. You will have to retrieve all the keys, 10 terabytes, and be able to send it in every node, because every node should have a match. So just, yeah, some vendor, some company will say, okay, we support SQL join and we do in-memory data grid. Yeah, they do, but at what cost? Okay, if I had to take 20 coffee to be able to have my response, that's not good for me. Okay, so normally you don't do SQL join. That's why, in fact, if you want to go from an in-memory database to an in-memory data grid, it doesn't work. Okay, you will have to. It's not a replacement. It's really you have to rewrite your application code because it's new paradigm. It's key value. It's different. So you had to do things differently. Up. And what about NoSQL? Okay, most of the SQL stuff are eventually consistency. Not all of them, of course, but most of them are eventual. In-memory data grid, sorry, it can be eventual, but normally it's consistent. Okay, so that's a big difference between the two. Okay, in-memory data grid has a too-fast commit protocol. Normally it's newer one. It's not the old. It's not the one you've learned in school. Okay, that's newer one, like the MVCC, so multi-version concurrency control. It's really an interesting topic because the idea here is really to have consistency at a really small price. Okay. So yeah, big difference that most of them are consistent, are non-eventually consistent, where in-memory data grid are consistent. So, for example, MongoDB has no in-memory feature, not at all. It's not a key value store. It's not an in-memory calculate grid. So if you want to do calculation on MongoDB, it's complicated. It can be complicated because if you had to retrieve all your key and do treatment on it, it just costs. What is interesting is that the move from Cassandra, so I guess you know what Cassandra is, but Cassandra till last year, had an in-memory feature, a smaller one. You can only have 1 gigabyte in memory, but that's a move. That's a move. Okay, I guess they will improve it on future version. But Cassandra now have a 1 gigabyte in-memory feature. So if you got really a smaller cache and you already have a Cassandra infrastructure, maybe you can see how you can use it. Okay, because it will be easier. But most of the time, you don't go from NoSQL to in-memory data grid to have a replacement. As I said, it's totally different paradigm, except if you use Memcache or Redis. Okay, but if you don't use key value store, it's not really a replacement. It's more a partnership. Okay. For example, if you want to speed up your Cassandra, okay, if you want to speed up your Cassandra, what you're going to do is you can put in front of your Cassandra an in-memory data grid. You will access to Cassandra using the read-through and the write-through or write-behind pattern, okay? But what's cool is that on your main data will be on the in-memory data grid and on MongoDB, so you will need to have twice the bytes available, okay? Sorry, I lose my... yeah, so it's a partnership. Up. So no, that's one. It's a partnership between the two. So in Cassandra, for example, you will do batch stuff because maybe that grid is not really good for batch, okay? It's not something that works really well. So you will use a Cassandra to do all your batch stuff, all your really large real-time queries because it was built with that on focus. You will do MapReduce activities on Cassandra, and on the in-memory data grid, you will be happy to have really fast access key value. You will be happy to directly have the object pass the object directly from the cache. Okay. will not have to constrict it or stuff like that. It's just serialization and deserialization. You will have in-memory SQL queries. You will also have MapReduce, but normally it's on smaller subset of data. Okay, for big one, normally people go more into Cassandra. But yeah, so really think about them. Of if you get a Cassandra, if it's kind of getting lower than what you want, just maybe you can use a cache or an in-memory data grid if you want to do calculation on it, computation. It can be a good solution, and that's normally what we do. Okay, in fact, in-memory data grid is more a partner to SQL and NoSQL, than really a replacement. Okay. What's really interesting is that if you remember the day before NoSQL, in-memory data grid were present. Okay, in-memory data grid is kind of old. Okay, but in-memory data grid is not really open source project. Okay, because the main target of open source project is bank and big companies. So 10 years ago, it was okay for them to pay a lot to have the features. Okay. But on the same time, we see that NoSQL appears and really was a success because I guess that now a lot of people use NoSQL stuff. So what is interesting is that to see that old in-memory data grid now start to be open source. Okay, the open source part of their core features, not all of course because they need to live and to do money, but you can really see a movement to open source. Now you've got Hazelcast, which has always been open source. But here, if you go to Hazelcast website, you will see that they put we are open source in big, because in the in-memory data grid market, you don't have a lot of open source player. Last year, we've got GridGain that was already a part of the project was already open source, but they don't have really a community on it, so they put it on Apache stuff. So you've got Apache in it, which is kind of new. They do the first release, I think maybe it was 2 weeks or 3 weeks ago. But now, yeah, you've got a movement in-memory data grid to open source. So for us, it means that we can test it more easily than to have a call to a vendor and have a guy that came at your office to do you a demo. That's not what you want. You want to see the stuff. You want to see the code. Okay, so that's an interesting move. I'm curious to see what will be the future. Will the move be? Will every in-memory data grid will try to open source a part of the product or not? I don't know. So if you got any questions, I've got 5 minutes, I think. Was it boring or? Just tell me. How many of you use, so you don't have question, I have got. How many of you use NoSQL stuff, like Cassandra, Redis? 2, 3, 4? Oh yeah, no, not a lot of people. Which one do you use?
Well, I use OrientDB with Hazelcast.
Hazelcast stuff, okay. Redis, okay. Okay, well, just some words about Redis. Okay, a few years ago, Redis was really good to do caching stuff. Redis is a key value store. Okay, but a long time ago, Redis didn't scale, not at all. So normally, but now, since version, I think it's version 3 of Redis stuff, you've got Redis cluster. And Redis cluster, if you want to learn something about scaling and Redis, you've got that's what they use at Twitter. So you just have to Google Twitter and Redis, and you will see how they scale, and they have been able to handle a lot of terabytes using Redis, and the engineers speak a lot about it. So it's really an interesting. If you can see them, it's really interesting talk. Okay, so thanks for coming, and have a nice day.